Section 1.3, Radical Expressions, and relatedly, toward the end we will discuss rational exponents. So, a radical expression is going to be something that contains a radical. So, the radical here is this little thing right here. The radicand in a radical expression is the expression underneath our radical. Now, our definition of what a square root means, the principal square root of a, is the non-negative number that, when multiplied by itself, equals a. It is written as a radical expression with a symbol called a radical over the term called the radicand. So, square root of a is our example. Now, a very common thing to have here, we're going to use this repeatedly, is that the square root of a squared equals the absolute value of a. Now, if a is positive, we don't need the absolute value bars, we drop those, but that will come up. So evaluate each of these expressions. Well, I want to try to write these with a power of 2, so I'm going to take 100, I'm going to write this as the square root of 10 squared, which, if you notice, I could also write that as negative 10 squared, but when I take the absolute value, that becomes a moot point. So then the square root here is the absolute value of 10, which is 10. That's probably something you've seen before. All right, now, for part B, the square root of 16, I'm going to write this as the square root of 4 squared. The square root of 4 squared is 4, so this is the square root of 4, which is 2. All right, part C. I can't write 25 plus 144 with a power of 2, but I can add those two. So this is the square root of 169, which is the square root of 13 squared, and therefore the square root is 13. Because if I take 13 to the second power, I get 169, based on the way I rewrote that. Part D, can evaluate each of these separately. So the first one is the square root of 7 squared. I'm going to go ahead and write minus the square root of 9 squared, so that we get 7 minus 9, or negative 2. All right, the product rule for simplifying square roots allows us to take a product. Okay, we have a product, square root of a times b, to make that the square root of a times the square root of b. Now, we can actually do this because of an exponent property that we saw in the last section. As we're going to see later in this section, we can treat square roots and generally any radical as an exponent. So this is actually an exponent property. If you remember, we had the product rule, a times b to the n equals a to the n, b to the n. Think of that to the n as a square root, and there you go. So let's simplify these. We're going to break these up into a pair of numbers that we can work with. Now, the way I'm going to work with this is I'm going to factor 300, okay, into its prime factorization. So 300 is 2 squared times 3 times 5 squared. Now, why would I want squared terms in there? Well, because our earlier property, the square root of a squared is just a. And you can verify that that's 4 times 3, 12 times 25, which is 300. So I can break this up into several squares. I'm going to change the order just a bit. This is the square root of 2 squared times the square root of 5 squared, based on our product rule, times the square root of 3. Now the first two become 2 times 5 times the square root of 3, or 10 square root of 3. Now, I could have skipped some of those steps, quite honestly, but hopefully you can see what I've done. I've broken it into 3 different radicals. 2 of those simplify to be integers, and then I can just multiply those integers. All right, part B, 162, a to the 5th, b to the 4th. When we have variables, things get a little bit more complicated, but we still want powers of 2 because we're dealing with a square root. Now, 162, I'm just going to go ahead and write this up here. 162 is equal to, actually I don't have that written down. All right, we've got 2 That would be 81. Okay, so that would be 2 times 9 squared, or times 3 to the 4th. There we go. So there's our prime factorization. Now I want this in with powers of 2, so I'm going to write the square root of 2 times 3 squared times 3 squared. Now for my variables, I want to break these apart into powers of 2. So this will be a squared times a squared times a. That way I have 5 a's. And then I'll make this b squared times b squared. Okay. Now all of the expressions with squared terms on them, with exponents of 2, can come out of my radical. So I'm just going to go ahead and simplify that. I get 3 times 3. 3 times 3, I have an a times a, which will be an a squared. And I'll have a b times b, that'll be a b squared. And remaining will be 2a. In fact, that's it, square root of 2a. So this simplifies to 9a squared b squared square root of 2a. The big thing to remember is we want to write these in terms with that have an exponent of 2. Right, simplify the following radical expression: the square root of 12 times the square root of 3. Well, this is going to require our property in reverse, so we'll multiply these two to be the square root of 36, which is the square root of 6 squared, which is 6. So 6 is our answer to example 3. Next we have the quotient rule, and again, this is actually an exponent property in disguise, but we can take the square root of a quotient and make it the quotient of the square roots. So we can start with 1 square root and end up with 2. Now this comes in handy when we have something like example 4. Simplify the radical expression, the square root of 5/36. Because 36 is a perfect square, as we've seen already, this is going to be the square root of 5 divided by the square root of 36. 36 is 6 squared, so this is the square root of 5 divided by 6. All right, this can work in reverse with example 5. Simplifying this expression, we can actually divide our expressions first. So let's just go ahead and write this as a quotient. 234x to the 11y divided by 26x to the 7y. Now if we divide that, we get the square root of 9x to the 4th, and our y's cancel, which this is 3 squared, x squared, x squared. So this is 3, and then we get x times x, so 3x squared. Example 6, add these two radicals. So what we're going to do is, if we have two things, I'm going to go ahead and write a rule here. If we have a square root of b plus c square root of b, if they have the same radical, or the same radicand in those radicals, then we can add the two of those coefficients together. That also works with subtraction. All right, so we can also do that with subtraction. So what we'll do is we'll simplify both of these and then see if they have the same radicand and the same radicals, and then we might be able to combine those. So 5 square root of 12, well, 12 is 4 times 3, so that would be 2 squared times 3. And 3 does not factor. It's prime. So this will become, bringing a 2 out, we get 10 root 3 plus 2 root 3. And combining those two together, we are going to have a root 3, and that'll be 12 root 3. All right, number 7, a little more complicated. First, let's go ahead and factor each of these. So 20, now 72 is 9 times 8, so that is 2 cubed times 3 squared. I'm going to go ahead and write this as a squared times a. times b squared times b squared times c minus 14 square root of, and that'll be 2 cubed a squared times a times b squared times c, breaking that into exponents of 2. Okay, now this right here, perhaps I should have written this as 2 squared. 2 squared times 2, so that we get 20 times 2 times 3 times a times b, square root of 2. Oh, that came out. I should have underlined those. 2a minus 14. And this over here, we're going to have the same thing happen. That'll be a 2 squared times 2. Let's clean that up. 2 squared times 2. Okay. So we'll bring out a 2, an a b times b, square root of 2ac. Oh, I left off a c over here. All right, so those two actually have the same radicand. We'll still want to simplify a little bit more. That will be 120 ab squared, square root of 2ac, minus 28 ab squared, square root of 2ac, and subtracting those two, 120 minus 28 is 92 ab squared, square root of 2ac. Now something I need to adjust is because there's one thing in here that we don't know if it's positive or negative. We know that b squared is going to be positive. We know that 92 is positive. We do not know what the value of a is. So all throughout here, once I took it out of my square root, I should have actually had that in absolute value bars to indicate that it is positive. So then our answer is 92, absolute value of a, b squared, square root of 2ac. Okay. All right, number 8. Write this expression in simplest form. 2 root 3 divided by 3 root 10. All right, well, we do not want a radical expression in the denominator. Okay, that's just going to be a rule of thumb. We don't want that to happen. So, how we can fix that is we can multiply by the root that is in our denominator. Okay, we'll see shortly why that works. This will be 2 root 30. This will be 3 root 10 squared, or 10 times 10. So the denominator becomes 30, and we have 2 root 30. Now the 2 and our 30 reduce, giving us root 30 over 15. Therefore, no radical in our denominator. That's a common thing that we're going to pull. Now, example 9 doesn't quite work the same because we don't just have a square root, we actually have a complex radical expression, 1 plus root 5. So what we're going to do is multiply by the radical conjugate. We're going to multiply by 1 minus root 5. Okay, now we're going to see more of this multiplying in the next section. But for the numerator, I'm going to distribute that. It'd be 4 times 1, so 4 minus 4 root 5. 4 minus 4 root 5. In the denominator, what I'm going to get, I'm going to multiply everything on the left side by everything on the right. So 1 times 1, which will be 1. Okay, 1 times negative root 5, so that'll be minus root 5. Next will be root 5 times 1, So I get plus root 5. Those two will cancel out. Root 5 times root 5, so I get minus 5. So I have 4 minus 4 root 5 divided by the two terms cancel in the middle. Those are a zero pair, and we get negative 4. Now, I can just divide by negative 4. That'll be negative 1 plus root 5. And that is my simplified expression. Now, up to this point, all we've discussed are square roots. But what happens if it's not just a square root, but it's a cube root or a fourth root? Well, that's where the principal nth root comes in. All right, so if a is a real number with at least one nth root, then the principal nth root of a, written as the radical with an n as an index there of a, is the number with the same sign as a that when raised to the nth power equals a. The index is that n. So rather than try to write things with powers of 2, we write them with powers that match the index. And in fact, the square root of a is just understood to be an index of 2. So we have been doing this the whole time. We want to write exponents. We want exponents in it that match the index. Simplify each of the following. The fifth root of negative 32. So what we want to do is write something to the fifth power. Now because we know that 2 to the fifth is 32, negative 2 is what's going to work here. And so the same rule that we had earlier will work. The nth root of a to the n equals a. Except we don't have to have absolute value bars there unless... Alright, so this equals a if n is odd, and it equals the absolute value of a if n is even. So the square root we had to have the absolute value bars. So this is going to be negative 2. Simple enough. All right, part B. We'll first use our product rule because that actually works for all radicals, regardless of the index. So this will be the fourth root of 4096. Now, 4096, its prime factorization is 2 to the 12. All right, so that is the fourth root of 2 to the 12. Now, if I write that with powers of 4, that is going to be 2 cubed times 2 cubed times 2 cubed times 2 cubed. I have 4 of them. So this ends up being, let's go ahead and write that. It's 2 cubed to the 4th. So we get 2 cubed, or 8, as our solution. All right, part C, negative cube root of 8x to the 6 divided by 125. To write these with powers of 3, I'm going to have my negative sign there. Cube root of, that is 2 cubed x to the 3 times x to the 3 over 5 cubed. So I get negative 2, and that'll be an x squared. I'll get an x for each of those terms, divided by 5. All right, part D. 8 times the fourth root of 3 minus the fourth root of 48. So 48, in its prime factorization, because we can't factor 3, is 2 to the 4th. Fourth root of 2 to the 4th times 3. So that 8 times the fourth root of 3 minus 2 and the fourth root of 3. We have the same radicals there. So this is 6 times the fourth root of 3. Next we have rational expressions, or rational exponents. Rational exponents are another way to express the principal nth root. The general form for converting between a radical expression with a radical symbol and one with a rational exponent is a to the m divided by n is the nth root of a raised to the mth power, and that's also the same as the nth root of a to the m. This is where I said the exponent properties is where we were having those, our product rule and quotient rule. Okay, this is how our exponents relate to this. So let's go ahead and write 343 to the 2/3 as a radical. Oh, I should notice, or I should point out here, the denominator is going to be our index. Our denominator is our index. Whenever you're converting between these. Okay, and our numerator is going to be our exponent. That's how those are related. So this is going to be written one of two ways. We can write this as the cube root of 343 squared, or we can write this as the cube root of 343 squared. Now that second one is a lot easier because that is 7. The cube root of 343 is 7. So this is 7 squared, or 49. Example 12, write this radical expression using a rational exponent. First, our exponent is going to be our numerator, so this is a to the 2/7, because our index there will be our denominator. And that would be perfectly acceptable, except we want this as just one rational exponent. We want it as simple as it can be. This would be a to the -2/7. I actually prefer the fractional form, the 4 over a to the 2/7, because of the positive exponent. But in our textbook, it actually has the negative exponent there. All right, our last example, example 13, simplify. We're going to use our exponent properties here. We will multiply all of our coefficients here, so 5 times 2 times 3, which will give us a 30. And then x to the 3/4 plus 1/5. So that's for our exponent property. Says when we're multiplying, we can add our exponents. Now that is 19/20. So 30 x to the 19/20. All right, and our last part for this, 16/9 to the -1/2. Now if you recall, negative exponents actually cause a reciprocal. Okay, they reciprocate some different things. So let's first go ahead and write this with the exponent on applied to both of those. 16 to the -1/2 over 9 to the -1/2. The reciprocating happens here, so we get 9 to the 1/2 over 16 to the 1/2. Now if you were to write both of those as radicals, these would seem much clearer. This is the square root of 9. Okay, we have the 2 to the first, or the first power and the second root, which is just the square root. And the same down here. So this is going to be the square root of 9 over the square root of 16, which is 3/4. All right, that brings us to the end of this section. So a couple of things to remember. One, exponent properties. They have not gone away. Because our radicals can be thought of as exponents, you can use all of those exponent properties. That's one really big thing. And the second is, a second thing we can say is whenever you are adding and subtracting, make sure you have the same radicand with the same radicals, okay, including the index. They must be the same. And then those product and quotient rules, those have some good special cases. Okay, those are special cases of those exponent properties that we use quite a bit with this.